Hi, I'm Dor Atzmon, a PhD student at Ben-Gurion University. This research is called Generalizing Multi-Agent Pathfinding for Heterogeneous Agents. This is joint work with Yonatan Zaks, Einat Kiviti, Lidor Avitan, Yonatan Morag, and Ariel Fellner. The multi-agent pathfinding problem is defined by a map with n locations and a set of agents, each with a start and goal locations. In this example, the start and goal locations of the green agent are A and F, and the start and goal locations of the blue agent are D and E. At each time step, an agent can either move to an adjacent location or wait in its current location. The task is to find a path for each agent such that the agent do not conflict, while minimizing the sum of travel costs. Here, we can see a possible solution for this example. In time step 0, both agents are at their start locations. Then, the agents move to location B and H. At this point, one of the agents must wait to avoid a conflict, and only the blue agent moves. The agents now move to locations C and E. And then, only the green agent moves to its goal location, and a solution of cost 7 is achieved. Multi-agent pathfinding is applicable in many problems, such as traffic control, robotics, and video games. However, in multi-agent pathfinding, the agents occupy only one location at each time step, while in reality, agents can have different sizes, and thus they can occupy more than one location at each time step. There were two important attempts that did not make this one agent per one location assumption. In multi-agent pathfinding for large agents, the agents occupy multiple locations and collide when two agents overlap. Each agent is represented by a reference point, for instance, the upper left corner. In this example, the agents conflict at time step t because when the reference points of the agents are at locations A and B, then both agents occupy location C. In this problem, the agents cannot rotate or change their size. In k-robust multi-agent pathfinding, the agents may experience up to k unexpected delays. Thus, the agents occupy each location for multiple time steps. In this example, the two agents conflict as both are planned to be at location C, and the difference between their time steps is less than k. In this problem, there is an assumption that the size of each agent is only a single location. The classic multi-agent pathfinding problem is extended by multi-agent pathfinding for large agents for agents of different sizes, and by k-robust multi-agent pathfinding for agents that can be delayed up to k times. In this research, we define a new problem, generalized multi-agent pathfinding, that generalize both of these variants of multi-agent pathfinding. In the generalized multi-agent pathfinding problem, we have the following new definitions. A state is a list of all occupied locations at a single time step, and the transition function gets a state and returns a set of m states. Each is a state that the agent reaches by performing an applicable action. In generalized multi-agent pathfinding, each agent gets start and goal states instead of locations and a transition function. And the task is to find a state's path for each agent instead of location's path. We can easily generalize large agents. The state of each agent is defined by the location it occupies at each time step. Here, the state of the green agent contains locations A, E, C, and F. Generalizing k-robust is less intuitive. The state of each agent is defined by its current location as well as its previous k locations. Here, the state of the green agent contains locations A, B, and C. Conflict-based search is a commonly used multi-agent pathfinding solver. First, it finds a path for each agent from its start location to its goal location. In this example, the path of the green agent is A, B, C, and F, and the path of the blue agent is D, H, C, and E. Then, conflicts are identified. Here, both agents are at location C at time step 2. To resolve the conflict, we split the node to two child nodes. In the left node, we have a new constraint that prevents the green agent from occupying location C at time step 2. And in the right node, we have a similar constraint for the blue agent. At step 4, we replan each of the constraint agents. Finally, we perform a best fair search on the constraint tree and expanding, for example, the left child. As it is conflict-free, it's a valid multi-agent pathfinding solution. For large agents, multi-constraint CBS was suggested. Notice that when the reference point of one of these agents is at location A, B, C, or D, then the agent occupies location C. To resolve this conflict, either the reference point of the green agent cannot be at location A, B, C, or D at time step t, or the reference point of the blue agent cannot be at these locations at this time step. For K-robust, KRCBS was suggested. To resolve this conflict, either the green agent cannot be at location C at time range T1 to T2, or the blue agent cannot be at location C at this time range. We propose GCBS for generalized multi-agent pathfinding. In this example, both agents occupy location C. This conflict can be resolved by imposing an occupation constraint. An occupation constraint prevents the agent from occupying a given location at a given time step, with its entire shape. Here, the state of either the green agent or the blue agent cannot contain location C at time step t. Using GCBS, we can impose an occupation constraint to resolve conflict between both large agents and K-robust agent. While the definition of an occupation constraint is simple, it resolves conflict in the same manner multi-constraints and range constraints resolve them. We ran experiments on 30 by 30 grids with 10% obstacles. The size of the large agents in this experiment is 3 by 3 cells. We can see that both algorithms, MCCBS and GCBS, almost achieve the same results in terms of success rate and planning time. We also performed a similar experiment for K-robust agents with K equals 2. Here also, both algorithms, KRCBS and GCBS, performed similarly. We talked about generalized multi-agent pathfinding and saw that both large agent multi-agent pathfinding and K-robust multi-agent pathfinding are special cases of generalized multi-agent pathfinding, and that GCBS performed relatively close to MCCBS and KRCBS. Future work can suggest policies for selecting conflict to resolve and can adjust GCBS for the case of probabilistic environments. Thanks for listening.